You hear this term all the time, right? Training an AI. It sounds like some kind of, I don't know, digital wizardry, but what does it really mean to train an AI model? Well, that's exactly what we're going to break down today. We're going to pull back the curtain and see what's really going on under the hood. At the end of the day, it all comes down to one thing: learning. But how in the world does a bunch of code, an artificial brain, actually learn anything? I mean, how does it get from knowing absolutely nothing to telling the difference between a cat and a dog? That's the big question here, and we're going to get to the bottom of it.
So here's our game plan. First, we'll cover what model training actually is. Then we'll look at it as an optimization problem. We'll talk about minimizing something called loss, use a real example to make sense of it all, and then we'll wrap up with what happens next.
All right, let's dive right in. What even is model training? The first thing you need to know is it's not magic. Not at all. It's actually a super methodical process. Okay, so imagine you've just built the structure for a brand new brain. You designed the neural network, you've set up all the layers and all the connections, but right now it's just empty. It's got all this potential, but it doesn't actually know anything yet. Training? That's the process that fills that brain up and actually makes it useful. So if training is what fills this empty brain, how does that actually work? Well, that brings us to the next big idea. At its core, training is really just one big optimization problem. It's all about finding the perfect settings for the network to work its best. Perfect settings, what does that even mean? Well, these settings are called weights. The best way to think about them is like millions of tiny little knobs, and there's one on every single connection between the neurons in this artificial brain. And here's the kicker. When a network is first created, all these knobs are just twisted to random positions. They're totally arbitrary. And that, right there, is the entire goal of training. The whole point is to systematically, methodically, turn all of those tiny knobs, to update these weights again and again, until you find that perfect combination, the one that makes the network really, really good at whatever you want it to do. Okay, but with millions of knobs, how does the AI know which way to turn them? A random twist just isn't going to work. Well, that leads us right into our next section: minimizing the loss. This is basically the set of tools the AI uses to figure out how to solve this massive problem. The main tool in that toolkit is something called an optimizer. You can think of it as an algorithm, and its one and only job is to watch how the network is doing, and then figure out exactly how to adjust those weights to make it better. And by better, I mean reducing the number of mistakes it makes. Now, there isn't just one optimizer. There are a whole bunch of them. But the most famous one, kind of the granddaddy of them all, is called stochastic gradient descent. We just call it SGD. The classic way to picture it is like this. Imagine the model's error, its loss, is a giant hilly landscape. SGD is the algorithm that helps the model take one small step at a time, always going downhill, trying to find the very bottom of the lowest valley. So what's the ultimate objective for an optimizer like SGD? Simple. Its entire purpose is to minimize what's called a loss function. Okay, so what on earth is a loss function? You can just think of it as a scorekeeper. It's a formula that measures just how wrong the network's guess was. It looks at the model's prediction, it looks at the actual right answer, and it calculates a score. If the score is high, that's a big error. If the score is low, hey, the model was pretty close. And that score, that's the loss. And now you can see how these two pieces fit together perfectly. The loss function is the referee that yells out the error score. And the optimizer is the coach that hears that score and tells the network exactly how to tweak all its little knobs, its weights, to get that score as close to zero as it possibly can. I know this can all sound a little up in the clouds, so let's bring it right back down to earth with a super common example: training a model to tell the difference between a cat and a dog. So here's how just one single pass in this training process works. Step 1, we take an image we know is a cat, and we show it to the model. Step 2, the model does its thing and spits out a prediction. Step 3, we compare what the model guessed to the real answer, which is cat. And finally, step 4, we calculate how wrong it was. We figure out the loss. But here's a really cool part. The model doesn't just shout cat, it gives you probabilities. So it might say something like, I'm about 75% sure this is a cat, but there's a 25% chance it could be a dog. Of course, we know the actual truth. The true label is 100% cat, 0% dog. And right there, that gap, the difference between the model's 75% guess and the 100% truth, that is the loss.
It's a real number that tells us exactly how wrong the model was on this one picture.
All right, so the model made a guess. We calculated its error. Now what? What happens next? How does this one single pass actually help the model to learn anything? And this, right here, is the absolute key. We don't just do this one time. Oh no. We show the model our entire collection of cat and dog pictures. And when it's seen them all once, we show them all again, and again, and again. This process gets repeated thousands, sometimes millions of times. This is where the magic, or, well, the method happens. The actual learning happens in this endless loop. See an image, make a guess, calculate the error, and then let the optimizer make a tiny, tiny adjustment to those weights. It's a bunch of small corrections repeated over and over that slowly but surely nudges the model toward being more and more accurate. So we've established that the optimizer's job is to turn the knobs to make the loss smaller. But how does it know which way to turn them? How does it use that loss score to make an intelligent adjustment instead of just a random guess? Well, that process is the real secret sauce at the heart of machine learning, and it's the perfect question to think about for next time.